Yo, so I'm Alex Ilgayev. Sorry for the delay. I will show you some really cool vulnerabilities that I found some of the most popular open source projects out there by inspecting their development pipelines. And cool. So let's start. Let's start with the agenda. Before we dive into what is these vulnerabilities, how they work, and how I managed to exploit them, let's start with understanding what is a GitHub Action, how does it work, why is it a powerful build system. Then we'll go through how it's possible to inject code by exploiting vulnerabilities in your GitHub Actions. I will show how I managed to develop some tools and to find these vulnerable repositories, how I reported them and mitigate these vulnerabilities. Show some demos, examples, and then how to mitigate this. So, about myself, I'm Alex Ilgayev. I'm working as a head of research in FreeCode. Previously, I led the malware research team at Checkpoint, where we're doing a lot of reverse engineering for complex malwares, hunting down cybercrimes, APTs. And nowadays, I'm researching mainly vulnerabilities in the software supply chain in FreeCode. In short, FreeCode is a cybersecurity startup company based in Tel Aviv that securing the entire SDLC pipeline of the organizations. So let's start. Has any of you been used or using GitHub Actions here? Cool. GitHub? Yeah. Cool. So there's quite a few. So what is GitHub Actions? So GitHub was all about storing source code, the most popular source code system out there. In 2018, they went in a different but quite similar direction by introducing GitHub Actions, which is a CI/CD, continuous integration, continuous deployment system that helps developers to automate their workflows from within the GitHub. It became extremely popular. It has extensive marketplace with over 18,000 custom actions out there, millions of public workflows. GitHub on itself has more than 100 million developers, hundreds of public repositories, and almost any ecosystem for development out there. There's some custom action that helps you to use GitHub Action for that. Okay. So why do you need it? How can you use this GitHub Action? So you could maybe create some simple automations to manage your code, to compile it, to build it, package it, push it to some cloud, some package manager, or whatever. You can scan your code for vulnerabilities, for secrets, for maybe for your dependencies that you are using in your code. You can run tests, unit tests, or whatever. Can label your issues to help you manage the bugs in your system, and many, many more. And how it's looked like. So this is like simple an action. It's a YAML file that contains a name, a trigger. In this case, the trigger is a push event. This means that every new code that introduced to the repository will trigger this workflow. And it contains also a series of jobs that each job contains steps. And this sample was a really simple echo hello world that does basically nothing, just prints that. And you just take this file and put it in .github/workflows directory in your GitHub repository. And that's it. As simple as it sounds. GitHub will automate this workflow for you whenever you push a new code to the repository. So before we dive into the vulnerabilities and how they work, we need to understand some core mechanics of GitHub Action and how it is working. So there's an entity they called GitHub Runner. This is the entity that runs the workflows themselves. It's an open source project maintained by GitHub, and it's just fetching the jobs from GitHub and simply runs them on whatever machine you want. And you can run it either on the GitHub hosted machine, which is the more popular method nowadays, or you can run it on some your self-hosted machine. If you run it on the GitHub hosted machine, you also run as an ephemeral environment. This means that every job will be created on completely a new and clean VM, a virtual machine. And whenever the job is over, the machine will be completely destroyed. It's a security measure. And also, there's an important aspect that's called GitHub token. We'll talk about it later. That's a new temporary token that GitHub creates for each and every workflow, and it helps the workflow to invoke some API calls with GitHub. So, what is this token and how it works? The popular method for accessing a GitHub API is creating some personal access token in the dashboard, and it has really high permissions, and it's a long-lived, so it can be leaked and expose your assets. So GitHub introduced this GitHub token. It has a default read and write permissions, but it's limited to the current repository you're working that you find your workflow in, so it's some security mitigation. And it also has time limited, so it works only while your workflow is running, or 24 hours at most. And it's also used as some common parameter for all the external action that you're using in your workflow, and some also an additional security mitigation. So if you're using GitHub, you're probably familiar with forks and forked pull request. This is the common method of contributing code to public repositories. You're creating your local version of the repository, creating your desired changes, and suggesting it as a contribution. So for this specific fork pull request that any user on the internet can do, so they are limiting the permissions for this GitHub token only for read permission at most, or else it will be a really critical security issue. And additional mechanism that in GitHub Actions, it's secrets. To create a meaningful workflows, I need to access my package manager, whether it's PyAPI, JFrog, Nexus. I need to access my cloud account, my AWS, GCP, or Azure account, and I need to store some tokens, some authentication for all these services. So I need to store this as secrets inside the CI system. So I can store this either on an organizational level that will be exposed to all my organization, to all my repositories. I can store this on a repository level, which is a more granular scope, or I can store it as a repository environment, which is something that we'll be talking later in the mitigations. So now that we've explored what is GitHub, how it's working, why it's very powerful, let's understand how can we be vulnerable, how can we find vulnerabilities in these workflows. So we'll take this example, really simple. It will be triggered whenever a new issue is created. Issue is a method in GitHub to handle bugs or maybe feature requests, or any user can add any issue he wants, just contain some text. And I create a workflow that will be run whenever a user creating an issue. And now we're running this simple script that checking the title of the issue. If it contains the word bug, so I'm invoking a GitHub API and adding label bug to the issue. This is a theoretical scenario in which I can help maybe triage issues that user creates. So this workflow also presents an additional mechanism in the GitHub Action, this double curly brackets, that helps the workflow developers to insert additional input data that GitHub service inserts. For example, we want to use this issue title, so we specify these double curly brackets with this syntax, and GitHub service replace this value with the actual value whenever the workflow is run. So we're using it for the issue title and for this GitHub token for the API to call the GitHub API. So on the first side, it's look very innocent workflow, doing no harm. But when you're looking at it deeply, this issue title is not sanitized properly, and any user could maybe insert some code instead of it and actually inject code into your workflow, right? So let's say I'm creating this issue name, looks very legitimately, not really, but it ends the quotes in that script, and just I'm continuing with my own script, and I'm creating this issue, and the result will be running my desired code, including printing this pretty psychotext. So this is a code that I'm, as a user, managed to inject through an issue title. It's quite insane. And I remind you that every user on the internet can create this issue for public repositories, right? So is it a bug? Yeah, that's why I asked myself. I went to GitHub documentation, and I understood not only it's not a bug, it's by design, and it's stated by GitHub that when we are writing new workflows, we should always consider whether our code might execute some untrusted input from the attacker. So GitHub leveraged that to ask the developers to secure our workflows. So then I thought myself, what can I do with it? Is it widespread? And maybe I can find maybe additional occasions of these issues. So I went to and use a quite new service by GitHub. It's called GitHub Code Search. It's a very cool service that I can find some code snippets in entire GitHub public repositories. So I created some queries, and I understood there's a lot of occasions that meet these criteria for this code injection. I just looked for this curly brackets, the run command, and I met hundreds of results. So some of these were quite popular repositories. I met several of these, and Liquibase, for example, is a really popular schema database changes tool that has more than 6,000 stars in GitHub. And on its own, it claims that it has been downloaded 75 million times on its website. So this has a real potential, this vulnerability. But we didn't stop there. We wanted to find even more occasions of these issues. And we wanted to GitHub Code Search wasn't enough for us, so we developed some tooling that we call it some GitHub indexer that practically downloads all the public workflows from GitHub. I'm talking about tens of thousands. We digested them to our homebrew graph database. And then we created some security context queries on that data, so we can find some more advanced, complicated vulnerabilities that contain several statements that each of its own doesn't pose a vulnerability, but together they are. And the results was really tremendous. We found an additional hundreds and even more popular vulnerabilities. We found that FreeCodeCamp, that it's the most popular repository on GitHub, was vulnerable. Storybook, one of the most popular front-end packages, NPM packages, is also vulnerable. You can see the number of stars for each package. FastAPI, one of the most popular packages for Python, a really popular web server. Fluent UI is a popular UI front-end framework by Microsoft. Xstate, it's an additional popular package by Stately. And many, many more. Slim Toolkit, Astro, AutoGlow, and it's a machine learning framework by AWS, and many, many more. So by understanding this entire surface, we wanted to divide this into some category classes, and then we will try to deep dive into some of them. So what did we see? We see first, issue injection vulnerability. This is the example that showed at start. Very critical. And the other class is vulnerabilities that's triggered by fork pull requests. This is the procedure that the developers are forking the repository and adding some new code. And in that fork pull request, there are several subcategories. We could inject into the pull request itself, into the title and description, just textual information. I could inject maybe into the branch. Whoever not familiar, so Git-based systems are separate into branches. There's a main branch and there are side branches. So while the main branch has usually some constant name, for example, main, the side branches are decided by the developer, so I can put almost whatever I want. There's few characters that are sanitized. I could maybe hijack through some code execution. Sometimes the trusting the code I'm pushing. Artifact poisoning, very interesting vector that we'll show later, and also third-party dependencies. So I will explore two of these use cases and we'll try to deep dive into how we were able to execute this exploitation. And then we'll also show some demos and how to mitigate these issues. So the first issue, the first repository, as I said, FreeCodeCamp. I'm sure maybe several of you are familiar with the project. It's the most popular project in GitHub with more than 300,000 stars. It's a platform to learn code. It comes with a great community. It's a very popular project. So, and I was able in this project to hijack the build because it was using a vulnerable third-party dependency, third-party integration. So this integration, it's called CodeC. So FreeCodeCamp was using CodeC that was vulnerable. And CodeC is a startup company that helps to visualize your code base in order to help you review your code easier. So how it works? FreeCodeCamp integrates with CodeC, and CodeC is creating a new workflow in a repository that runs on every pull request you're doing in your repository, and it visualizes the changes that you made to the repository to help you review it faster. So this workflow had issue, and we will show some of the issue that it has. So it's in short, this workflow is checks out your code, downloaded your code, and runs some action, some CodeC map action. And when we dive it even deeper, this CodeC map action is running some CodeC package, some NPM package. And one of the input parameters of that package is the branch name. It was very interesting because the branch name is user controlled. Maybe they are not sanitizing it properly. So we were investigating it a bit even further and tried to play with some branch input, putting quotes, semicolons, trying to give it some weird variables. And suddenly we see a crash. And when you research vulnerabilities, crash is always welcome because it means something bad happened, but good for you. So seems like by the output log, seems like it tried to execute something that's called ECH, which is part of your branch name. So maybe it's susceptible to a branch injection. So after playing a bit with the payload, we created this very nasty payload that giving permissions to some file and execute it. By the way, this brackets, IFS brackets, it's to overcome the limitation that they are not allowing spaces, and it actually replaces spaces in the Linux shell. So if I give the CodeC this branch name, what do I get? I get a code execution. So I managed to, because they weren't sanitizing it properly, the branch injection, I managed to execute and to execute my own desired code and just practically whatever I want. So what is the attack flow in this example? So as I said, FreeCodeCamp integrated CodeC. I can see it because it's public repository. And I'm as attacker first, I'm forking the project. I'm creating my local version of it. I'm pushing my shell file, shell.sh, doesn't matter. I'm creating a malicious branch name, the one I previously showed. And I'm suggesting pull request. And that's it. Without any user intervention, it triggers automatically, and I can just hijack the build and do whatever I want and run whatever I want. So we worked closely with CodeC because FreeCodeCamp weren't the only users that were using. There was a lot others that were using it as well. So we were working with closely and closed all these vulnerabilities. We even suggested them to harden this workflow even further to reduce the permissions, so nothing like that won't happen again. So this is not vulnerable anymore. The second example is Fluent UI. So Fluent UI is a popular UI framework by Microsoft. It practically powers the entire Microsoft 365 suite, including Word, Excel, Outlook, Teams, you name it. So it's a really important repository for Microsoft. And we managed to find there an artifact poisoning vulnerability. So how it works? So Fluent UI has two interesting workflows, the screener build job and the screener run job. So screener build job can be triggered by any user, and it doing some tests and it builds some artifact. And the screener run job is triggered only when the build job is over. And it takes the artifact and deploys this screener application that helps the developer somehow to visualize the changes. So the vulnerability was that the screener run job, the ones that receives the artifact, and I'm, as a user, the only control I have is this artifact. So whenever they take the artifact, they also put it in the root directory and overwrite any file in that directory. So this means I have the primitive to overwrite any file for that workflow that has been checked out previously. So how can you use this primitive to get code execution? I don't know if you're familiar with web development, but there's a file that's called package.json. That's contains all the packages, all the npm packages that you are using whenever you deploy some application, and it also contains some scripts. So if I will override this package.json file, so that workflow, whenever it runs the build itself, it deploys in the artifact, it runs this yarn install, it automatically takes this package.json file and it runs all my desired scripts. So this could be my ability to execute code on the runner. So let's see how the flow looks like. I'm as attacker, I will fork the pull request just as previously. I will update it, the screener build job to create my desired artifact that I want to poison. I will put there my package.json with all the scripts I want to execute. I will just create this pull request and this will trigger automatically the workflow without any intervention. This job will build my malicious artifact, will be passed forward to the second run, and it will I will able to hijack the build. So after discovering this vulnerability, we talked with the MSRC, Microsoft Security Response Center, and they said that it's the first time they're meeting that kind of vulnerability, but they acknowledge it, and of course they fix it later. So you could think of yourself maybe, so what's the point of all this? What is the actual damage that I could cause by hijacking this build? I mean, what kind of sensitive information there is? But there is, as I previously said, you're using this build to access all kinds of your assets, your cloud providers, your package managers, your source repositories, or almost anything you want to do. So it contains a lot of tokens, a lot of secrets, a lot of authorization tokens that you could just exfiltrate and steal them. Also, as I said, this GitHub token contains default write permission. So if I getting a foothold of that build hijack, I could, commit back to the repository and write whatever I want without having the proper permissions. A much smaller risk will be maybe the ability to run botnets or crypto miners or whatever on the runner infrastructure. So to understand how I'm able to execute all this malicious behavior, I created some simple lab environment using the popular ngrok tool, very recommended, especially to pen testers. It allows you to create a TCP or HTTP tunneling back to your computer. So I created this ngrok endpoint. Then I ran netcat, simple netcat listener to create a reverse shell from the runner, and I have this simple reverse shell payload that I sent as part of my, for example, issue injection payload, and the result will be that I will get back a reverse shell back to my that's be tunneled through ngrok back to my lab computer. So how it looks like, for example, let's say I'm sending this really simple issue title that contains this reverse shell payload with the ngrok endpoint. I will get a complete reverse shell from the runner. So it will help me to explore the run, to understand how it works, maybe do some reconnaissance, to improve my exploits later, and maybe do some security research. So let's show you some demos into how we can do this. I have another simple workflow that will be run my demos on it. It checkouts the code and do several prints, but the point is these prints can be injected. So we'll show how I'm able to inject and do malicious behavior on this workflow. So you could ask yourself, this GitHub token, where could I get it? I don't see it anywhere in the workflow. But it's quite subtle, but whenever I run the checkout command, it also sends automatically, by default, this GitHub token to download the repository. And I don't know if anyone knows, but whenever you're using some authorization token to check out, to clone your code, it also saved in the Git configuration file. So I'm as an attacker could practically just print this Git configuration file, find this authorization token, go pipe it through a basic C4 decoding and get my token. So let's see how it's possible to do it in demo. So on the right, I have my simple HTTP server in my lab environment that will be showing all the messages. On the left, I'm creating this issue in GitHub in my demo repository containing the payload that sends the GitHub token to my server and through the ngrok. So you can see that I received this token on my server. This is the GitHub token that I extracted and exfiltrated from the pipeline. This is quite simple, but let's show you something more complicated. Let's show you how it's possible to do that with branch injection attacks. So I'm setting up my server again. Now I'm forking the repository, creating my local version of the repository. It should take a few seconds. And then now I'm modifying this repository. I'm creating my shell file or whatever I want to execute. In this shell file, I'm just sending my token, and now I'm creating a new branch, and this branch contains also the payload that showed previously that executing this shell file. And now that I finished creating my local version, my local payload, now I'm suggesting this as a pull request to the main branch, to the so-called public repository. And once I'm creating this pull request, you can see that the workflow runs automatically without any human intervention, because that's how it was defined in the first place. And once it runs, you can see that I got this token that managed to exfiltrate from the server. So for the demo, we will show how you're able to commit malicious code to the repository, back to the repository. So on the left side, there's a really simple Git configuration files that commits and push the code. It's nothing fancy there. On the right, there's the code that will be running in the runner. The code is basically just fetching this script that commits the code, giving it the right permission, and we're just running it with the file we want to commit. So let's see that in demo. So this time you can see a simple demo repository with only a directory and a file. And now we are creating a new issue, and this issue also will contain the payload. So this payload, as I said, is fetching this script that commits the code, giving it the right permission, the execute permission, and then just run it. So when we go back to the repository, we can see we have an additional file, we call malicious file, that our workflow managed to push. Even further, you could also notice that the commit message, that the committer was somewhat called maintainer name, and the commit message was innocent commit message. So I'm able also to control this information whenever I'm doing a commit. So I can impersonate anyone I want if, of course, commit signing isn't being used in the repository. So these are the demos. So let's see in short how we're able to mitigate all this risk. So first of all, Avoiding run steps. Run is like simple bash scripts. You can inject there whatever you want. It's recommended to avoiding it whenever you can. For that, you can use external action. For example, instead of calling API for updating the label, you can just use some external action that was developed by the community that doing precisely that, which is a lot harder to inject there. So even when the title in the right example, even when the title will contain some code, it won't be run because it's sanitized as a string. Another method is to sanitize your input as an intermediate environment variables. So instead of using this, for example, the title and the body inside the script, you can define it outside the script as some intermediate environment variable and use that variable in the script. So because it's simple bash script, you can't inject code to the environment variable. So it will be sanitized. There are additional methods. Another effective method specifically in GitHub Actions to mitigate any post-exploitation is to limit permissions. For example, in our method, we want only to create issues, to update issues, so we can state in the workflow, this is the permissions we need. And even if you contain some, other vulnerabilities and attacker managed to exploit them, he won't be able to perform whatever you want because he won't have the right permission for that. For secret exposure, secrets are the tokens that can be exfiltrated, so you can control them and to what repository has access to this secret. So whatever repository that doesn't need your AWS account secret, so you can define that so it won't be exposed. And there's also the additional method for requiring approval for outside collaborators. So when I say that workflows are run without any human intervention, you can define that it will require someone to go through the code before it's being run automatically, so we can also protect you from such attacks. And final method, there's something that's called environment. It's mainly in GitHub Enterprise that creates a stronger protection for your secrets and for your workflows by defining specific permissions on who can run them. Yeah, so let's talk about the takeaways and summary of the talk. So first of all, you need to understand that if you're using CI/CD and using some development workflows, you need to understand that your build pipeline could be compromised. There's a scenario for that. Also, that GitHub Actions platform delegates many of the security to the developers. I mean, you have ephemeral builds, you have a lot of security features in your VMs, but still a lot of the responsibility is on the developer. I'm a developer myself, and I know that you can do mistakes, so it should be handled. The consequences can be quite severe. The CI/CD part of the development pipeline is one of the most sensitive parts. It has access to a lot of secrets, a lot of code, so it should be also handled carefully. And finally, securing your pipeline is a matter of faith. As I said, there's a lot of mitigations options, and you have the right tools. GitHub provides you the right tools to do it, and that's it. So thank you very much. Some of the publications and for the background of this research could be found in the PsyCode website. You're welcome to scan this QR code is safe. Don't worry. And that's it. So I'm open for questions now, later, whatever you want. Thank you. Yeah. He dies, yeah, but your virtual is like stacking the run, so you can do whatever you want. I mean, when you're finishing the reverse shell, so it's finishing the runner machine as well. But during the reverse shell, you can do whatever you want. Yeah.
The secrets you get access to, the ability to override files into the main branch, then other developers pull out their code.
you're asking if the secrets that I get access in the build can override the main branch, right? Yeah, it depends on the secrets. I mean, there could be secrets that give me access to, I don't know, GitLab or Bitbucket, or secrets for GitHub, or secrets for any possible system. So yeah, practically they give you also potential access to the main branch. Yeah. Yeah. Yeah, that's one of the consequences of this. Yeah.
GitHub documentation for that is that you shouldn't use that in combination with untrusted code for doing anything that executes like builds or tests, because that runs in the context of the fork repository as opposed to the context of the merge commits on origin.
Yeah. So you're right. In the example, I use pull request target, which is the less secure version of pull request, and which gives you a bit higher permission. So without that, I would able to execute this demo. But on the other side, many repositories nowadays use it. So all the vulnerabilities I found were using this pull request target. So yeah, there's a version which is a bit more secure, but doesn't allow you to do all the added value of the pull request target. It gives you like less privileges.
GitHub has some good documentation for on not running untrusted code using pull request target the other day, as well as that has suggestions for how you might be able to use untrusted code in combination with like a workflow dispatch.
Yeah, so there are sources in GitHub that helps you like to make your code more secure, specifically on that part. But also there's a lot of documentation in GitHub, so I don't think every developer in every company is aware that of all these security best practices. So, the content is out there. I mean, if you want to secure your workflow, you can find all the desired content to do that. Yeah. Yeah, the question is, are there any free linters to parse and find issues in the source code? So yeah, I'm aware of two, I think, of SemGrep. It's a very popular static analysis tool. I think it has. No, I think it has a built-in rules for securing GitHub Actions, and I also a scorecard by OpenSSF. I think they also have several rules for finding this. Yeah. Yes. Yeah, but it goes back to the same question of best practices in code or in any other aspects of the development. Yeah, I don't think that developers are to blame for not following this, because also specifically for open source project that they don't always has their enough enough means and time to take care of all this. So it's very hard to blame them for that. Yeah, but we are in some process that I think that security and development are try to meet somewhere, specifically in the DevOps area, because DevOps are also sometimes developer and also had to take care of the security. So I don't think it's separate teams. It's something of the culture that we need to educate developers to take care of security. We need to educate security teams to to understand development teams, not to stop them and not to delay them too much. But I don't have an easy answer for that. It's a really complicated issue. Yeah, thank you very much.